Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss interfacing of digital to analog converters with 8086 using 8255, which is PIO, Programmable Input Output Device, or we can call it as PPI, Programmable Peripheral Interface. The slides and contents are prepared by referring the textbook Advanced Microprocessor and Peripherals, authors A.K. Ray and K.M. Burchandi, publication Tata McGraw. The analog to digital converters, which is predominantly known as DAC, convert binary numbers or digital data into their analog equivalent voltages. At the output side, the DACs may give voltage or current as output. The desired output level is voltage. So if you get current, that we have to convert into voltage. The DAC find applications in areas like digital control gains, motor speed controls, programmable gain amplifiers, and few waveform generators. The commercially available DAC is 0800, which is a monolithic 8-bit DAC manufactured by National Instrument. The supply for DAC 0800 extend from plus 4.5 volts to plus 18 volts. The reference voltage for plus V is minus 5 volts to plus 1 volts. And reference voltage is for minus V is kept at minimum voltage of minus 12 volts. The typical schematic of a DAC 0800 is shown in figure. The signal whichever it is going to generate, which is in the analog form, for the equivalent binary numbers which are provided on the bit lines bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. So whatever the value which you are passing on these lines B7 to B1, that it will be converted into output current that we can get from IOut. So by connecting some current to voltage converter at the output side of 0800, we can get equivalent voltage for the given binary numbers. A typical interface of DAC 0808 with 8255 is shown in figure 2. So from microprocessor, we want to drive a DAC. As 8086 is not having any ports, we are going to take one interface device, that is 8255. So first the processor will send the digital value which we want to convert into analog signal. This 8255 will be given the digital data which we are getting from the processor to DAC. This will generate at the output side either current or voltage. So by using a proper device, we can convert the current into voltage. Here on left hand side, we are going to have a processor. We are taking 8086. This 8086 will give the digital values on the lines D0 to D7. This 8255 will send this digital data which is given by the processor to the DAC 0808 through port A. So either you can use port A or port B or port C. So in this case, I am taking port A. The port A is used to pass the digital values to the DAC. Based upon the values which we are receiving on B7 to B1, these values will be converted into equivalent current at the pin 4. This is given for inverting amplifier, so which at the output side we can get a voltage as output. The reference voltage, which is 5 volts, is given to the pin 14. The plus V, we can connect between plus 5 volts to plus 12 volts, whereas minus V we can connect to minus 12 volts. Next, this 741 is a op amp which is used to convert the current to voltage. To enable 8255, we have to enable the chip select by corresponding interface circuit. We have to proper the value 0 by based upon the address. Next, once this is activated, the data which we are getting from 8086 will be passed to DAC through port A. So for this 8255, we are using only port A, that is also in the output port, whereas the port B and port C, these we are not using for DAC. Now we will see a programming concept for generation of different waveforms using a DAC 0800. The problem statement is as follows. Write an assembly language program to generate the following waves of frequency 500 Hz during the interface DAC with 8086 using 8255. The 8086 system operates at 8 MHz. The amplitude of the triangular wave should be plus 5 volts. The waveforms which we are going to generate is square wave, ramp or sawtooth wave. The third one is triangular wave. So before writing the assembly language program, first we have to find the control word register value for 8255. The general format for 8255 control word register is shown in table 6. The LSB is port C. In this example, the port C we are not using, so this bit is a don't care. The port B also we are not using, so this bit is also a don't care for interfacing DAC. As we are not using port B and port C lower, the mode for group B is also a don't care. The port C upper also we are not using, whereas port A we are using, that is also in the output port, so we had to write this value is equivalent to a 0. The mode of operation here we are selecting is mode 0 for port A, and as it is IO mode, we have to write the MSB value as 1. So this is for to configuring 8255 in IO mode. These two bits are 00 for mode 0 for group A ports. This bit is 0 for configuring port A as output port. The last 4 bits are don't cares. Either we can take the values from 00 to 1111, any value we can take, whereas the upper 4 bits are 1000, which will give 8, whereas here I can have 0 to F. So the control word register value I have to write for 8255 either 80H or 81H like this till 8FH, anything we can write. As the lower 4 bits are don't cares, we can write the control word register value as 80H to 8FH, any combination we can write. So I am selecting the default values for all the ports. I'll select as zeros. As they are don't cares, we can pass any value. I'm taking 0. So the control word register value I'll take for DAC is 80H. So the control word register value we are writing as 10000000H for control word register, that is 80H. Now for writing the program for DAC in 8086, the first statement is for a generation of a square wave, where square wave is having 2 voltage levels. One is 0 voltage, the next one is maximum voltage, I'll take as plus V. So this 0 voltage will maintain for some amount of time, T1 I'll take, and this wave is kept at plus V volts for some amount of time, that I'll take as T2. If T1 is equivalent to T2, we will get a symmetric square wave. If T1 is not equivalent to T2, we will get a asymmetric square wave. So depending upon either we want to generate a symmetric waveform or asymmetric waveform, pass this 0 voltage for T1 amount of time and plus 5 volts for T2 amount of time. So as DAC is 8-bit DAC, for 0 voltage, I'll take the bit pattern as 000 for 0 volts and 1111 for maximum voltage. So we will pass 00H for some duration T1 amount of time. FF we will pass for some amount of time, that is T2. Here in this program, I want to take a symmetric waveform. So I'll represent T1 is equivalent to T and T2 is also equivalent to T. So I'll generate a symmetric waveform. For generation of symmetric waveform, we are going to be passed only two values for DAC. One is for generation of 0 voltage by passing 00H on the port A. For generation of 5 volts, we are going to be passed the digital value as by providing each and every bit is equivalent to 1, that is FFH for some amount of time. So for symmetric purpose, I'll take the delay value as same for both the periods. Assume the delay program is already existing. So the program will start by initializing the segment for code for the by using the directive assume CS colon code. Then we will start the code segment by using the assembler directive segment directive. We will write as code segment. Start up the program with the start. The first step we have to write is updating the control word register value with ATH. So for writing the ATH into control word register value, first we will move this ATH into AL register. By using out instruction, we will move this one to control word register. So for loading ATH into AL register, we will use move AL comma ATH. This AL contents which is ATH, we have to direct to control word register by using out instruction. The instruction we will use is out control word register comma AL. So actually in place of CWR, we have to place actual address of control word register. So I am taking a generalized notation. In CWR place, we have to replace the address of control word register. So wherever I am referring as port A, port B, port C or control word register, it is the address of that particular port or register. Next, we have to pass 00. For passing 00 for port A, first we have to load into AL register. So for that, we will write move AL comma 00H. Then we have to move this 00H for port A. For that, we will write the instruction as out port A address comma AL. So this 00 we have to validate it for some amount of time. So for that, we will call a delay program. For calling a delay program, the instruction we will use is call delay. So this delay program will be written depending upon how much time we want to make this one as 0. Once it is generated for a t amount of time with logic 0 or voltage 0, then we have to raise this one to plus V volts. So for moving or plus making output voltage as plus 5 volts, we have to move the FF value into port A. So for updating port A with FFH, so first we will write move AL comma FFH. This value we have to pass for port A by using the instruction out port A comma AL. Then we have to maintain this FF value for some amount of time T. So this we will get by calling a subroutine with the name delay. So to call a subroutine, the instruction we will use is call delay. So these three instructions are used for generating a logic 1 or plus V voltage for a duration of T. So once this waveform is generated for one cycle, if we want a continuous waveform, again go for a sending 00 for port A. So here we will write a unconditional jump for loop 1. So JMP L1. So whenever this instruction is encountered, the processor will take the control to move AL comma 00. Again 00 waveform will be passed. Wait for some amount of time. Again FF will be passed to generate logic 1 for some amount of time. So this will be repeatedly executed. How many cycles we want? That many number of cycles. So if you write JMP instruction, it is going to generate a continuous amount of square wave. If you want to limit, you can place a counter for every waveform generation. You can decrement the count, then you can go for JNZ instruction. So here I am taking a program for generation of a continuous square waveform. So I'll terminate the program by writing INT21H by calling a subroutine at 4CH. So move AH comma 4CH INT21H code end is to end the code segment. To end the program, end is the directive, end label for start of the program, that is start. So this is a program for a generation of a square wave. The various instructions which you are given is first writing control word register, then passing 00 to port A, wait for some amount of time by calling delay program, then generation of FF value to generate plus V volts at the square wave for some amount of time. For continuous iteration of the square wave, we are writing jump L1. If jump L1 is removed, then it is going to generate only one waveform. If you write JMP L1, it is going to generate n number of pulses. This is the program for generation of a square wave. The next program is for generation of a sawtooth wave. In the generation of sawtooth wave, if you observe the waveform, this wave is changing its value from 00 to FF linearly. First we will pass 00, then 01, 02, like this it will be extended up to FF. Once it reaches to FF, again it is going to start from 00 to FF, 00 to FF. So as we required a delay program in square, here delay program is not required, because for each and every instant we are going to be pass some value for port A for generation of the square wave from 0 volts to plus 3 volts. So the logic for this one is the control word register we have to write with 80H, then 00 will be passed to port A, then we have to pass 01 to port A. Like this it has to be sent total 256 values from 00 to FF for port A. So when you pass 00 to FF values, this will generate a waveform is like this, which you can take as a ramp signal. If I want to get a sawtooth wave repeatedly, the same values we are going to be passed repeatedly, so that you can generate a sequence of or number of pulses which you can take as sawtooth wave. If it is a ramp, a single value or single iteration is enough. For generation of sawtooth waveform, we have to run the program for multiple number of times. So first we will start by calling the directive assume for code segment, that is assume CS colon code of code segment. To start the code segment, we use the directive segment, that is code segment. Start up the program with updating the control word register with 80H. So first we will move 80H to AL register. So start colon move AL comma 80H. Here start is a label, it is optional. Then this 80H we have to move to control word register by using out instruction. So next instruction is out control word register comma AL. The first value we are going to be pass is 00. So this 00 will pass to AL register, move AL comma 00H. Then this value we have to direct to port A. So we write out port A comma AL. Then for getting the next value, which is 01, we go for incrementing AL. Up to FF value, we have to pass this. So we will compare the AL content with FF. Compare AL comma FFH. So now if you see from 00 to FF, the values here it is very less. So here it is going to generate the carry flag is equivalent to 1. So whenever carry is equivalent to 1, it indicates the port A is less than FF. Go for writing the value to port A. Whenever FF is done, that means this waveform is generated. Again we have to initiate from 0. right? Compare AL comma FFH. So whenever it is satisfied, it will come out of the loop, that is JC. So here we will write a JC for checking carry flag is equivalent to 1. Whenever carry is equivalent to 1, it indicates the AL contents are less than FF. So first we have to send 0, 0, then we have to send 0, 1. As 0, 1 is FF less than FF, so the control will be transferred to label 1, where we are going to be transfer the AL contents, which is 0, 1 to port A. Then increment AL, that is next value it is going to be 2. It will compare with FF. As 0, 2 is less than FF, it is going to generate a carry flag. So as carry flag is equivalent to 1, this will be redirected to loop 1. So this loop will be iterated repeatedly for generation of the waveform from 0, 0 to FF. Once it reaches to FF, this condition fails, then it will come out of the loop. When this will come out of the loop, then again we go for generating the next wave starting from 0, 0 to FF. So we will write jump L1. For terminate the program, move AH comma force H, INT 21H. To end the code segment, we will write code endes. To end the program, end stop. So this is a program for generation of a sawtooth waveform. For generation of a ramp signal, the JMP instruction we can omit, which will generate a simple ramp signal. For generation of a square wave, sawtooth wave, we have to generate a pulses repeatedly. That's why we'll write JMP instruction. So here the program which we wrote for generation of the sawtooth waveform in the inclining ascending, right? Suppose if I want the waveform is like this, I want to generate a square sawtooth waveform for generation of the sawtooth wave is like this. So here, what is the first value we have to send is FF, then we have to send FE, then we have to send FD. Like this, it has to be continued until 0, 0. So in this program, a small modification you can do, that is instead of writing 0, 0, here you can pass FF value. Instead of increment, this you can write as decrementing. Instead of comparing with FF, we have to compare this one with the 0, 0H. These three steps we have to take for a generation of the sawtooth waveform in the declining manner. So JMP L1, it is for a continuous iteration of the loop, so that we are going to gen n number of pulses. The next program is for generation of a triangular wave. In the triangular wave, we have to generate the wave first increasing, later decreasing, again increasing, later decreasing. So starting from 0, 0, we will pass 0, 0, 0, 1, 0, 2 like this until FF. So when you are moving in this direction, the value of this we are going to be increment. Once it reaches to FF, again it has to be decline, that is FE, FD, FC like this until 0, 0. So here the contents of AL will be incremented for getting this decline. So we have to go for decrement. So one is a generation of a sawtooth wave inclined manner. One is for generation for sawtooth or ramp signal in the decline manner. So by combining this, we'll get a triangular waveform. So for a generation of a triangular waveform, we have to pass the control word register value as 80H first. Then we have to pass 0, 0 till FF. Once it reaches to FF, again we will run in reverse manner, that is decrementing till 0, 0. For continuous waveform, again incrementing from 0, 0 to FF, again decrementing from FF to 0, 0. We will start the program by declaring a code segment through the assembler assume directive. Assume CS colon code. Start off code segment by the assembler directive segment, that is code segment, to start off the program with the label start. First control word register value we have to write with 80H. So for this, first we will move 80H into AL register by using the instruction move AL comma 80H. This AL contents, which is ATH, we have to move to control word register by using out instruction. So we use out control word register, comma, AL. Next, we have to pass the initial value as 00. For passing 00 value, we will move 00 to AL register, that is move AL, comma, 00H. This value we have to direct to port A by using out instruction. So we will write out port A, comma, AL. For the getting next value, the next value we have to pass is 01. For getting this, we go for incrementing AL content, that is INC AL. This increment will be takes place until FF. So we go for comparing AL contents with FF. So compare AL, comma, FFH. So if AL content is less than FFH, which it is going to be make the carry flag is equivalent to 1. So if carry flag is equivalent to 1, that means the next value we have to pass. So go for looping. Otherwise, else, that is if carry flag is equivalent to 1, so you can exit the loop. So for writing this logic, we use JC instruction. If carry is equivalent to 1, go for label 1. So when it is carry is equivalent to 1, if the AL content is less than FF, somewhere here it is going to be lies. So when AL content is less than FF means here we are going to be lies in this region. So then you go for this label, send that value. So this will be repeated repeatedly until AL contents is reached to FF. Once it reached to FF, then we have to go for declining manner. So first that FF value we have to pass to the output by using the out instruction. Out port A, comma, AL. FF value is passed. Once FF value is passed, then we have to write FE, then FD. Like this, it has to be continue until 00. So for getting the next value, we have to decrement AL contents. So by using the instruction decrement AL, we will get FE, that is next value. Next, this value we have to compare with 00 to indicate the end of the program. So we will write JZ loop 2. So this instruction either you can write in two manner. One is compare AL, comma, 00H. Then we have to jump to loop 2 whenever it is not 0. Whenever it is not 0. So instead of writing this compare instruction, this same functionality we will get by decrement AL itself. So no need to go for comparison again. So that's why I omitted compare instruction. JZ loop 2. So what is this JZ loop 2 will get is the decrement of AL will be takes place until AL is non-zero. When AL is non-zero, the Z flag is equivalent to 0. So when AL is non-zero, we have to go for iterating. So here we have to write this one as JNZ L2. So whenever AL content is equivalent to 0, Z flag will be 1. Then we have to come out of the loop. So this will be repeated until FF to 00 is generated. So till this point, you are going to get a one waveform. If I want repeatedly, then we go for label 1, where the label 1 it is used for generation of the waveform from 00 to FF again. So again we are rewriting this. So this will be executed repeatedly for generation of a sequence of a sawtooth waveform. To end the program, we will call INT21H by moving AH with 4CH. Move AH, 4CH. Call software interrupt INT21H. End the segment, which is code segment, by using the directive endes related to code. So we'll write code endes. To end the program, we use the directive end start. So this is a program for generation of a triangular wave. The logic which we have used is first initialization of control word register, then passing the value from 00 to FF in an increasing manner. Once it reaches to FF, come back this one until 00 by decrementing the AL contents. By going a JMP instruction, we can generate n number of pulses. So here the instruction is JNZ. So with this, I'll end the session. That is digital to analog converter interfacing with 8086 using 8255. In this session, we have discussed writing a program for generation of a square wave, for generation of a sawtooth wave, for generation of a triangular wave. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.